Oh, wait, they're back in the lobby again. All right. Okay, addition and subtraction. So we were talking about floating point numbers. Now, floating point numbers are a bit strange, right? And the reason they're strange is because they have, sorry, this is Teams is being really annoying. Okay, the reason they're strange is because floating point numbers occupy a fixed amount of memory, and you're trying to represent something. So you're trying to represent real numbers, which can have an arbitrary number of digits. So there's always going to be some sort of imprecision when you work with floating point numbers. We had in the last lecture, I described to you a floating point format where we have a fixed number of digits in what's called the significand. Right? So we always use 3 digits to write out we always write our floating point numbers always use 3 digits to represent an integer number s, right? And then we use another digit whose value is between -5 and 4 to represent the exponent. All right. Now, when you go to add two floating point numbers, what you need to remember to do is that you want to write both numbers in their floating point format so that they have the same exponent. Right. So when we add 12.1 and 63.8, right, when I write them out in their floating point format, I don't have to do anything special because their exponents are the same. Right. And this just lets me add the significands together now. Right. So I add 121 and 638. Right. That gives me 759. The exponent doesn't change. Right. Similarly with 81,500 and 13,600, I can simply write them, when I write them out in their floating point formats, the exponents are the same. So I can just add their significands together to get 951 times 10 to the 2. Now, when you do the sum or the difference, right? The sum or the difference can contain more digits than the two operands, right? Than the two numbers that you're adding or subtracting. So when they contain more digits than the two numbers that you're adding, right? So here we've got 4 digits in the result. You round the result. Right? So instead of 1459 times 10 to the -1, right? You round that so that it has 3 digits in the front. So that's 1460, right? Times 10 to the -1. And then you adjust the exponent so that there's only 3 digits in the significand. You get 146 times 10 to the 0, right? Which is just 146. Similarly here, when you add 81,500 and 93,600, right? The intermediate result is 1751 times 10 to the power 2, right? Round that result and then adjust the exponent to get 175 times 10 to the 3. Now, when the operands have different exponents, right, that's when we, for our purposes, that's when we do something a bit strange, right? You take the number with the smaller exponent, so in that case, that's 12.1, right? Because 4,320,000 is 432 times 10 to the 4, right? 12.1 is 121 times 10 to the -1, right? So we take the number with the smaller exponent, scale the exponent up so that they match, and then adjust the significand, right? Now notice we no longer have 3 digits in the significand. So when we do our sum, you have to deal with these digits after the decimal point, right? So here we've got 432 point a bunch of stuff, right? I've only got 3 digits, so I just lose the bunch of stuff to get 432, right? To actually do this, though, you need 8 digits to compute the result, right? Which means if you're doing this in hardware, and your hardware is designed for 3-digit numbers, right? You need to somehow produce extra digits to compute the result, right? And in hardware, that's expensive to do, right? At least in the past, it was expensive to do. Today, it's not it's much less expensive to do. Right. So if you discard all of the digits from the previous example that are after the decimal point, right, then notice that y becomes 0. Right. So when you add a large number to a small number, it's possible for the small number to not contribute to the sum at all. Right. In other words, x plus y is equal to x, where y is not equal to 0, right? Which is a mathematical contradiction, but it's simply a fact of life when you work in floating point. I'm pretty sure I did all this, so I'm just quickly going through the slides again. If you don't have the extra digits, this can produce large errors when you measure the errors in ULPs. Right. So, for example, when I do this difference here, right, because I don't have the extra digits to represent the 0.8 here, right, I lose the 0.8, right, and then when I do the difference, I end up with an error of 80 ULPs. Right, which is very large because we're supposed to be able to add numbers with a half ULP precision. So it turns out you do need extra digits to do the sum and maintain reasonable precision. Right. So if I keep one extra digit, right, so if I use a fourth digit, keeping the digit after the decimal point, right, I can get the true result of the previous example. Right. This is the actual correct result of this difference here. A single guard digit's not sufficient to ensure a half ULP error, though. Right. So in this example, I'm going to subtract 110 and 8.59. Right. So we write out 110 in its floating point format. Right. 8.59, I do the same thing, but its exponent is smaller than the exponent on x. Right. So when I write out 8.59, I get 8.5. Right. I only have one extra guard digit, so that 9 gets lost. I do the difference, I end up with 102. Well, I end up with 101.5, so I round that result to 102. Right. The true answer is 101.41, so that's a difference of 0.59 ULPs. Right. So it doesn't quite get me the 1/2 ULP error that I'm looking for. So it turns out you need to use 2 digits. Right. So if I use an extra digit here and here and here, you can mathematically show that you always can compute a difference or sum to within a half an ULP. Right. So it turns out you need 2 digits, 2 guard digits, if you're working with decimal numbers. All right. So this is where we got to at the end of last class, I think. So one of the strange things in floating point arithmetic is that you can end up with this phenomenon called cancellation. So when I take two floating point numbers, and I subtract them, if the two numbers have similar values, then you end up with what's called loss of significance or cancellation. Right? They both mean the same thing. So here I've got a floating point format where I have 10 digits. Right? These two numbers are very close together. Right? So this one is exactly 1. Y is exactly 1 less than x. Right? If I subtract these two numbers, right, then I end up with the value 1 times 10 to the 0, right? Which when I write as a floating point number, looks like that. Okay, now up here, I've got 9 significant digits. Right here, I've got 10. Right. The difference, the final answer though, only has 1. Right. So there's only one number here, and the rest are all trailing zeros. Right. So I've only got one significant digit here, even though my inputs have about 10 digits of significance. Right. And so that's why it's called loss of significance. Right. When you subtract the two numbers, all of these digits here, right, here, they end up canceling one another. So the leftmost digits, or what are called the high order digits, or the most significant digits, right, they cancel one another out, and that leaves only the rightmost digits, or the low order digits, or the least significant digits. Right. Now, in this example here, the answer is correct. Right. So if I do subtract these two numbers, you do in fact get 1. Right. So yes, there's cancellation, but there's no impact on the final result. Right? So if the two inputs, if they have no error, right? So in other words, if their floating point representation matches their actual representation, their actual values, then we say this is benign cancellation, right? In other words, yeah, we're subtracting two numbers that are close together, so we should get a small number. The problem happens when your two operands contain error caused by the floating point approximation. So if I want to subtract two numbers x and y, but I had to compute x and or y, right? Then there's a good chance that x and y contain some sort of floating point error in them, right? Because every time you do something with a floating point number, you run the possibility that there's error in the computed result. So when this happens, catastrophic cancellation can occur. It doesn't always occur, but it can occur. Right. So suppose I want to compute the roots of a polynomial. Right. So there you use the quadratic formula. Right. So b squared minus 4ac. Okay. So I have to compute b squared. Right. That's b times b. I have to compute 4 times ac. Right. When I compute these two values, where b, a, and c are all floating point numbers, right, the final answer, the result of b squared and 4ac can be imprecise, right, because of floating point error. So let's work out this example using, let's work out what the answer is, right, using real math, so using actual mathematics, right? So let's not do this using floating point, right? So I'm going to use actual math, right? So I'm going to take 3.34, square it, multiply all this out, right? You get these two numbers here, right? Notice these two numbers here, that's got 7 digits in it. This has 6, right? When I compute the final result, now this is interesting. So the final result only has 3 significant digits in it. So this is an example where I can represent the final result. If I was trying to do this in floating point, I cannot represent the intermediate result, right? Because I can't represent those two numbers exactly. Well, the real answer is 292 times 10 to the minus 4. Now, what happens if I actually try to do this in floating point? Right. So I compute b squared, right? I get that. Can't represent that number exactly because it has too many digits. So I round the intermediate result to my floating point representation. Right. So in other words, I round this down. I round this so that it only has 3 digits. So I get 112. I do the same thing with this value here with the value of 4ac. Right. Too many digits here. So I round to get 111. Right. Now I subtract that value and that value. Right. And I get 1 times 10 to the minus 1. When I normalize that, that's 100 times 10 to the minus 3. Right. By normalize, I mean my floating point representation, I'm not allowed to have leading zeros. So I have to move the 1 to the front of the number. Right. That means adjusting the exponent. Right. And notice I get that number, that value there. And the surprising thing in this result here, right, that's 100. That's 292. So none of the digits in the computed answer are correct, including the most significant digit, right? The leftmost digit is wrong. The other digits are wrong, and even the exponent is wrong. I can't even compute the answer to the correct order of magnitude in this case, right? Which is kind of surprising. But when I compute the error in ALPS, right? So how do I compute the error in ALPS? So this is 292 times 10 to the minus 4, right? That's 100 times 10 to the minus 3. To get the error in ALPS, I take the smaller number and scale it, right? So that the exponents are the same, right? So whenever you compute the error in ALPS, you need to make sure your exponents are the same, right? And now I subtract the two significands. It gives you, when I take the absolute value, you get 708, right? So that's an error of 708 ALPS, which is enormous, right? The two intermediate answers are supposed to have errors within half an ALP, right? So b squared, right? That's within half an ALP. right? So the difference is 0.4 something, so I'm within 1/2 an ULP. Here, difference is 0.264, so again, that number there is within 1/2 an ULP of that, right? So my two computed inputs, they are as accurate as I can compute them using my floating point format. But when I combine them together to compute a difference, my answer is wildly off, right? So I went from having two numbers with 1/2 an ULP error or less. When I subtract them, I end up with 708 ULPs of error. That's catastrophic cancellation, right? So this is one of the implications of using an imprecise, of the imprecision of floating point, of our floating point representation. Right? So when you subtract two values that are close together, and the two numbers that you're subtracting are computed values, then there is a possibility that the final answer is very far off from the correct answer. Now, there are cases where you're computing something with some sort of mathematical formula, and you can transform the formula so that catastrophic cancellation is avoided. Right. So there is a possibility that this can happen. The notebooks contains examples of this, right? So this isn't really a math class, right? So this isn't this isn't a class on numerical computation. So I don't really want to go into these examples in the lecture. I'm also not going to ask you about them in any quiz or exam, right? But if you want to see some examples of how you can use math to rewrite the formula you're computing to avoid catastrophic cancellation, there are some examples for you to work through in the notebook. Now, there are cases, one of the more common cases where you run into the imprecision of floating point is when you sum a bunch of values together, right? So imagine you have a list or an array of values and you want to compute the sum of all the values in the list or array. Right? This turns out to be very common because if you want to do any sort of statistics on the numbers in your list, right, like compute the average or its standard deviation, right, then that basically involves summing all of the values or summing a bunch of values that are computed using the values in your list. Right? Now, every time you do a calculation with some floating point numbers, right, that operation potentially has a 1/2 ULP error. Right? So if I sum n values, right, or if I sum n plus 1 values, right, and all of those values have some sort of floating point error in them, then you potentially end up with n over 2 ULPs of error. Right? So, for example, if you sum 1,001 numbers, you potentially end up with 500 ULPs of error, right? Which is not great. Right? So here's an example where that you can actually run. So if you type this into Eclipse or your favorite Java IDE and run it, you can see that when you compute the result, you're going to get that number there. So you're going to get 1,125,000, even though it's very easy to see that the correct answer ought to be 1,100,000. Right. So we're off by 25. We're off by 25 in the computed answer. So here I'm using an array of float. Right. Now remember what float is. Float is the floating point type that has less precision than double. Right. The only reason I'm using float here is so that I don't have to add more numbers to show you a big difference. Float has less precision than double, right? If you use double, you'd have to sum more numbers together to get an interesting answer. So here I've got an array of 1,001 floats, right? I'm going to put the number 0.1 in for all the values of the array, and then the first value I'm going to set to 1,000,000, right? So I'm going to add 1,000,000 plus 0.1, plus 0.1, plus 0.1, plus 0.1, where there's 1,000 0.1s. Right? So 1,000 times 0.1, that's 100, plus 1,000,000, so that should be my final answer, What's the difference between a float and a double, except for the fact that float expresses a smaller domain of it. That's the difference. That is the main difference. So float uses 32 bits, a double uses 64. So that's the main difference there. There's no other difference. They both exhibit the same. Why would you use float? So if you have lots and lots of numbers that you need to represent, and memory is an issue, then you would use float. Right. Similarly, there are certain applications that don't require the extra precision you get with double. So in other words, you can compute stuff with float, and the answer that you get is still acceptably accurate for your purposes. Right. So those are the two main reasons. Normally, you use double, unless you have some other reason not to. Double. So if you have a floating point number, use double unless you're told otherwise. That's true in general, actually. If you in a language like Java or C, normally you default to double unless you have some reason not to. Is there a reason to use the F instead of a point? Yeah, if you have float and you want to write a literal, right? So if I want to write the value 0.1 as a float, you have to include the F. Because if you don't include the F, Java thinks it's a double, and then it'll complain. It'll say, I'm trying to stuff a bunch of doubles into an array of float. So the F here is important. Right. Any number with a decimal in it that does not have an F at the end is a double, as far as Java is concerned. The same is true in C. And Python, I believe, is also true. Any other questions? All right. So what am I doing here? I'm just going to compute the sum, right? So I'm going to use a for each loop to compute the sum. It doesn't matter if you use a regular loop, you're going to get the same answer, right? When you print out the result, you get that. Now, the reason you get that should be pretty clear or fairly obvious at this point, right? So the way I'm computing the sum is I've got a million at the very front. Right? So a million, and then I'm going to add a relatively small number, right? 0.1 is several orders of magnitude smaller than this, right? So I'm going to have a million plus a small number, right? So when you add a small number to a much larger number, right, you lose some of the precision of the small number, right? I now have a million and something that's almost 0.1, right? And then I add another small number to it, right? So I lose some of the precision in the 0.1, and then I add that to 0.1. Add 0.1 back to that larger number, right? So I keep on losing some precision in the 0.1s that I add, right? If I started with 0.1 though, and added 0.1, those numbers have the same order of magnitude, right? So when I add those together, the final result will be very close to 0.2, right? In other words, I lose much less of the precision when I add 0.1 and 0.1 together than I would when I add 1 million and 0.1, right? So if I just reordered this array, right, so that I stick the million at the end instead of putting it at the front, right? Now when you run it, you get the correct answer, right? Which again is weird, right? I'm adding all the same numbers together, but I change the order in which I add them together and I get a different answer. Right? So this is another one of the weird things that you encounter when you work in floating point. Right, so the problem occurred because I started out with two numbers that were very different in magnitude when I added or subtracted them together. Right, so sometimes you will see advice that says if you need to sum a bunch, or if you need to do something with a bunch of numbers, right, a bunch of floating point numbers, right, then you can reduce the error in the final result by sorting the numbers that you want to add together. Right, so sort them from smallest to largest and then do the sum, right? Now, this isn't a great solution, right? Because sorting has complexity big O log n, right? Whereas just to sum n values together, that should have complexity big O n, right? Furthermore, the constant that's in front of this n log n is normally quite large for sorting. So you've turned a problem, which should be in big O n, into a harder or more complex problem, which is now in big O n log n. Right? It's actually worse than that, right? Because you have to sort and then add all the numbers. Whereas it would be nice if I could just add all the numbers. Now, the other problem is so suppose you write a library routine that you make available to everybody else. Right? And your library routine promises to compute the sum of a bunch of values as accurately as possible. Right? And then inside your routine, you go ahead and sort everything. Right? So someone who calls your method with an array of values or a list of values, right? When your method returns, their list is now sorted, and they may not have wanted that to happen, right? So in other words, if you do take this approach where you sort the values and then add them together, right? That has the side effect of you end up with a list of sorted values, and the order of the values might have been important for some other reason. So this is also another problem. Now you can get around that problem by copying the array and then sorting the copy, but that's now even worse, right? So now you have to make another copy, which takes another big O(n) extra memory, right? Plus big O(n) time to make the copy, then n log n to sort, and then another O(n) to sum, right? So that's not a great solution either. I don't want to go through this in the lecture. And I'm not really going to ask you about it on an exam or on a quiz. But there is an algorithm that's written by this guy named Kahan. So Kahan is one of the architects of the IEEE 754 standard. He's also Canadian. Yeah, he's also Canadian. And he is very, very well known in the area of numerical computation. He's also a Turing Award winner, I believe. So for those of you who don't know, the Turing Award is the highest award in computing. So he's one of those winners. So he's very well respected for his work in floating point or numerical computation. Sorry. Oh, there's an algorithm that can actually do this sum in big O(n) time. Right. So the notebooks actually go into some detail on how the algorithm works and why it works, if you're interested. That's all I want to say about floating point numbers, right? So for our purposes, what are the important things to remember, right? So you should be familiar with the floating point format, right? So you should know that floating point numbers are represented as some integer times either 2 or 10 times to raise to some integer exponent, right? On a quiz or an exam, it'll always be times 10 raised to some exponent, right? Because I'm not going to make you guys work in binary on a quiz. But on your computer, everything's base 2, right? Everything's binary. So on your computer, it's actually some integer times 2 raised to some integer exponent. Right? The fact that floating point numbers have only occupy a finite and fixed amount of memory means that there is imprecision in your floating point numbers, right? They can't represent every real number. And then you need to know how to compute things like what is the error between two values, right? In ULPs, you need to know what an ULP is and things like that. Right. All right. Any questions on floating point? All right, so move on to the next lecture. Actually, if it's okay with everybody here, I would like to end the lecture here because there is something I need to take care of. I don't like doing this, but there is a bit of an emergency that I have to deal with. So if everybody's okay with this, I'd like to end the lecture 20 minutes early. Everybody okay with that? Anybody opposed? No problem. Okay, thank you. I'll post, so I will post a recording of the lecture, and we'll start a fresh lecture on today's Tuesday, Thursday. Right. Yeah, there is another lab coming up, but again, because of the deferred exams and the fact that I had to mark like 80 of them, I'm a little bit behind. Right? But there will be a lab coming out later this week. All right. Okay. Thanks everybody. Sorry about the short lecture, but there is something I need to do. Thanks. See you Thursday.